tutorial, we are going to learn about junior PAM, which is also known as pulse amplitude modulated fluorometer. So, before using this particular instrument, we should know its working principle in brief. So, basically, junior PAM is a pulse amplitude modulated or PAM chlorophyll fluorometry along with saturating pulse analysis of fluorescence quenching has become a standard method for evaluating various photosynthetic parameters. In the 1990s, the world's technique PAM or PAM 200 was introduced this technology in the university classroom. Junior PAM measures chlorophyll fluorescence to evaluate photosynthetic performance, particularly the efficiency of photosystem 2 or PS2 or we can say PS680. It is widely used in plant physiology for detecting plant stress and evaluating various photosynthetic parameters. Chlorophyll A, as we all know that chlorophyll A is very important molecule in photosynthesis. So, chlorophyll A fluorescent kinetics is widely used as a method for studying photosynthesis in plants, algae and cyanobacteria, which offers both qualitative and quantitative information. Various techniques such as PAM fluorometry method analyze fluorescence changes during photosynthesis, which basically measures rapid rising and slow declining phase in dark adapted samples or when they are exposed to light. The fluorescence induction curve, or we can say OGIP transient, plays a very important role in measuring chlorophyll fluorescence. So, basically it comprises of label O, which we can say as origin, Ji, which are the intermediate levels, and then is P, which is peak. These changes are inductive of the reduction of photosynthetic electron acceptors. The fast phase of this chlorophyll A fluorescence induction, or we can say OGIP transients, is widely studied due to ease of analysis and compared to a slow phase. So, basically this phenomenon is closely linked with photosystem 2 or we can say PS680, where variable is chlorophyll A, where variable is basically chlorophyll A fluorescence, which originates from photosystem 2 and it is influenced by electron acceptor sites. So, here plastoquinone or we can say QA act as a quencher. When it is in its oxidized stage, plastoquinone basically act as a quencher. So, the fluorescent rise reflects the reduction of quencher A or we can say plastoquinone A. Whenever there is rise in fluorescence, then plastoquinone reduced itself, and this will basically affect the redox reactions and there will be a photosynthetic electron transport chain. So, now what happens in OGIP? The OGIP transient now provides valuable insights into photosystem 2 photochemical quenching and electron transport activity, and it also affects various inhibitors, strators and mutations. Additionally, several factors such as photosystem 2 connectivity, P680 oxidation, pheophytin, plastoquinone pool and non-photochemical quenching and electric field can also modulate fluorescence. So, basically these are various parameters which can change fluorescence accordingly. We are going to take two samples, one is dark adapted sample and another one is light adapted sample. So, basically what happens in the dark adapted samples, here PS2 reaction center remains open. So, in dark adapted samples, PS2 always remains open, which results in minimal fluorescence, which is known as F0, and it is represented by O. Here O stands for origin, as we have explained in OGIP curve previously. The rapid OJ rise is driven by photochemical process and it strongly depends on light intensity, while the slower Ji and IP phase are associated with thermal processes. Under saturating light, when we are keeping our sample in dark light condition, then their fluorescence reaches its peak and we name it as FM or F max. When all the plastoquinone molecules are reduced, we are giving our sample a light, then all plastoquinone molecules are reduced and this will close photosystem 2. In dark adapted condition, photosystem 2 was open, while when all quinone molecules are oxidized, then photosystem will remain closed. Then a lower light intensities will change fluorescence little bit. Now notably, analyzing fast fluorescent induction curve under saturating light using parameters like F0 and Fm provides the critical information about photosynthetic efficiency and activity. So we are going to take F0 and Fm. Basically these will provide us insights that whether there is change in photosynthesis or not, or whether PS2 activity is working properly under stress condition or not. So moving forward, as I have told you earlier, that we are going to work on two samples. First one is dark adapted sample and another one is light adapted sample. So basically in dark adapted samples, minimal fluorescence or F0 and maximal fluorescence which is Fm, we are going to study them, and we are basically going to study whether there is change in it or not and how much change we are seeing in healthy stressful conditions. Then we are going to study a ratio of Fm and F0. Basically ratio of Fm and F0 remains constant under different physiological condition, but only under non-stress condition or when our plant is healthy. But when we are giving any hormone treatment or when we are subjecting our plant to any stress, then Fm upon F0 ratio do change. The difference between Fm and F0 is referred to as variable fluorescence or FV, and FV by Fm ratio is commonly range between 0.78 to 0.84 in higher plants. So this is the range which is provided, that FV by Fm ratio should be 0.78 to 0.84 in higher plants. Basically this is the indicator of maximum quantum yield of PS2 photochemistry. Now another useful parameter, that is relative variable fluorescence, which is particularly at time t. So it is defined as Vt and it equals to Ft minus F0 upon Fm minus F0, which normalizes the fluorescence induction curve for comparative analysis in various parameters, whether we are taking control or hormone treated or stressful plant. So moving next to a plant, when the sample is subjected to light, then what happens? So basically here, whenever the plant is light adapted, then there is change in PS2 activity or PS2 regulates itself. However, exposure to intense light pulse results in temporary fluorescence maximum, which is F dash max, which is generally lower than Fm. Obviously, F dash m will be lower to Fm. We are going to take out Fm where? In dark adapted sample, and in light adapted sample, F dash m will always be lower than Fm. Non-photochemical quenching, or we can say NPQ, is quantified by the expression of Fm minus F dash m upon F dash m and comprises of three components. Basically NPQ has three components. One is QE, which is also known as an energy dependent quenching, then is QT, which is state transition quenching, and then is QI, which is photo inhibition related quenching. So here energy dependent quenching component is rapidly reversible and associated with thylakoid membrane and delta PH, PSBS protein and zeaxanthin, while QT results from reversible photophosphorylation of light harvesting complex 2 or PS2. So these are various parameters which we are going to study in light adapted samples, that are NPQ, QE, QT, F0 by Fm, various parameters you will study here. Then you can compare your samples and you can say that what are the changes you are seeing in controlled condition, in hormone treated plant and stressed plant. So dark adapted samples are commonly used as reference point to a normalized data from light adapted samples. We are always using dark adapted samples as our reference point, and however, light adapted samples, we are going to sample them and note their readings, aiding its derivation parameters like Qn and Qp. So this is the junior PAM. As you can see here, we are going to demonstrate it in detail. So what are its application? Basically, junior PAM is used to monitor whether plant is in stress, that is drought, salt or temperature extremities. What are the photosynthetic change that we can measure by using this junior PAM, and how we can use this in our crop improvement researches and studying the impact of environmental changes on plant health. Now, advantages of this junior PAM, as you can see that we can measure here in real time measurement. We can measure here and we can take reading from here only. Secondly, it detects early photosynthetic alterations. As we know that photosynthesis is divided into two major components, that is light reaction and dark reaction. So early photosynthetic alteration we can study here while using this junior PAM. Suitable for different plant types and environment. We can study on different plant varieties or different plant species, and we can study it in different environments also. It provides detailed information on photochemical and non-photochemical processes. Apart from that, it is a compact device and it can be easily used in field studies. So this is a brief about junior PAM. So now I am going to tell you that how to use it. So basically, this is the junior PAM. It's too handy as you can see it, and I have connected it with this laptop. In this laptop, we are already having its software, and so I have connected this junior PAM with this laptop, and we are having here this very delicate fiber, and we have connected this delicate fiber here. Its one end is connected to junior PAM device and another end is connected to its sensor. These are magnetic clip, or we can say magnetic sensors. It will sense that what are the changes we are going to see. Basically, this magnetic sensor is used to study, or is used for studying of dark adapted sample, while this clip is used to study samples which are light adapted. So I am going to demonstrate you that how we can study it. Here we are having this, we can also take out this fiber from it. Okay. Very meticulously, you just have to close it. Now, what are dark adapted sample and what are light adapted sample? Basically, we have covered our leaves 30 or 45 hours prior to experimentation. We have to cover our leaves with foil paper. So when we are covering our leaf with foil paper, then this leaf is getting no light, means it is dark adapted. It is starving. Here photosystem 2 is open. So whenever we are going to remove this foil and light will fall on it, means the PS2 will activate itself, and plastoquinone quenching will start to its peak. So we are going to get FM of F max here when our sample is dark adapted. Okay, so how to take its reading? Firstly, we have to remove. Firstly, in this laptop, let me show you. Yeah, these are tomato plants. We have to select all the desired parameters which we are going to take. Suppose I am selecting all parameters. Suppose we are going to take QP, QN, QL, NPQ, Y, F naught, FM, and FP by FM. This particular set is already calibrated. These are tomato plants. This is hormone treated plus stress. This is control one, and this is stress. Now we are going to study that what alteration we are going to get. So firstly, we'll study in control set. So basically in control set, we are going to remove this foil and gently we are going to put this clip. It should be flat like this. Then here we are going to read our reading by clicking on set. So whenever we are going to click on set, then we are going to get here readings of different parameter. As you can see, FV by FM and FM. No, another parameters are not included here because this sample is dark adapted. Okay, so here we are getting reading of FV by FM as 0.375. It's too low because we are not getting light here, enough light. When we are working on field, then this reading would be, I think, in range of 0.765, but we are not getting enough light, so we are getting here reading of 0.375. Is it clear? Now we can move to another sample, but firstly you have to take it out very gently and close it. Now moving to next sample, which is our stressed plants. Very carefully you have to put this magnetic clips in between and place leaf in between. Now again same procedure, we are going to click on set, and again here we are getting readings of 0.211. So this means in control plants our FV by FM is 0.375, while in stressed condition it changed to 0.214. So FV by FM values are declining. Now moving forward to hormone treated plants, as these plants are having dust and dirt particles, this should be clean. Neither your readings will. Now this plant is hormone treated. So what are you thinking, that FV by FM value should increase? Then this control set. So let us see. Again we are going to remove this foil from our leaf. And then here we are going to click on set. You can clearly see that in hormone treated, FV by FM is 0.736. So it is clearly seen that in control set, FV by FM is 0.3, here 0.1 and here 0.736. So these are samples which are dark adapted. Now moving to light adapted samples. So what we have to do, we have to just take it out, clean it, then we have to move it, take it out, take our fiber out from it. Then we have to insert this fiber into this clip. This clip is basically used when we are going to study light adapted samples, and this particular magnetic one is for light adapted samples only. We have We can take any leaf starting from hormone treated only. Now here we can take different form of reading. Suppose I am going to take F0 by Fm. Then whenever I am clicking on F0 by Fm, only I'll get reading which is F0 by Fm. But when I am clicking on set, then I'll get reading which is QP, QN, QL and NPQ. So firstly, by clicking on F0 by Fm, so here by clicking on F0 by Fm, Fe by Fm value is 0.714. So why it is lesser than dark adapted Fe by Fm? Whenever plant is in hunger, so all the PS2 is open already, so all the light will strike on it, and basically all plastoquinone will start getting quenching. So we will get Fe by Fm always more in dark adapted sample than in light adapted sample. So here we are getting 0.714, which is hormone treated plant. We can also take set here. By set light, we can get different readings such as, here we can get different readings such as QP, QN, QL, NPQ. It totally depends on you that whatever reading you have to take. Suppose if you only have to take Fe by Fm, then no need to go for this all. But if you want to take QN, QL, then you can take by using this. Now moving to next, which is stressed plant. As you can see that morphology of this plant is already here we are getting 0.277. Reading is 0.277. Obviously, Fe by Fm is lower than hormone treated plant. Fine. So you can compare here that Fe by Fm declined in stress treated plants. Now, if we talk about control set, then in control set we are getting Fe by Fm reading 0.632. Again 0.632 is lower than hormone treated plant. Apart from that, NPQ is 0.013, maximum yield which is Y is 0.500, QN is 0.021. So if you want to incorporate these readings in your data, then you can, it's totally depend on you that whatever readings you are going to take. Apart from this, we can also see light curves here. If you want, then you can go for it, but here you can easily see that in report we are getting all these kind of readings, which is on this side we are getting Fe by Fm, and then Fm, then F0, NPQ. So we are getting different readings. Whatever you want, you can work on it. Fine? Or again I should explain. Is it clear? So it's very, I think it's very simple one. Apart from that, you can save your data very simply as you save data in MS Word. Just you have to click here on file and then save this data on desktop. It's quite easy. Now you all can come in SAM 10, 10, group of 10, 10 and वही वही होगी रीडिंग सारी। वो ग्राफ तुम लोग को अपने डेटा में थोड़ी करना है, ये नया पैम है ना इसलिए, ये नया है, इसमें तो तुम रिपोर्ट दे सकते, रिजल्ट यहाँ से कर्व्स करके है। हटो, कम आएगी। तुमने खाना नहीं खाया है, तुमने खाना नहीं खाया है तो क्या हो,
used for generating smoke water. So this equipment has been prepared by myself, and I was induced by the history of hurricanes, as I told you yesterday, that in Australia, in jungles, the fire forest was a common phenomena, as in recently in California, the jungles were burned and huge loss of property and forest was done. So the scientists examined in Australia that next year of the fire forest, there was a very luxurious generation of plant and very healthy growth of the plant was found. So they found that smoke, particularly the smoke formed by the burning of twigs, leaves and wood, it created some chemicals which are known as kerikins. So these kerikins are helpful in increasing the germination of plant as well as the general performance of the plant. Okay. So I read the whole story and then I prepared this equipment by myself. So first I purchased a suction pump from USA. That was not very expensive. And then I purchased a hot plate from Mumbai. And then the rest of the setup was prepared over here. So unfortunately, the suction pump which I purchased from USA was defected and it was not working. So I purchased a new suction pump today. And instead of using a hot plate, today I am using induction plate or induction cooker. You are familiar with this induction cooker because this works only on the steel utensils. Okay. So only on the steel it works, otherwise aluminum or any other material it will not work. Okay, ceramic or aluminum or other copper like that, it will not work. So for this purpose, this is more cleaner than using the hot plate. I purchased a induction cooker, induction heater, and then I took a utensil of steel as a bowl to hold the straw because I am preparing the smoke from the straw, wheat straw. Wheat straw were purchased from the market and then I washed it, dried it in the oven and all the moisture was removed in the micro oven. So the whole straw was completely dry. When it was dry, I poured into the steel utensil and covered with a funnel, and the funnel was connected to the suction pump. Okay. The funnel was connected to a flask, a suction flask, okay, in which the glass tube was gone to the bottom, and the flask was filled with the DDW, okay, and the pump was turned on, suction pump was turned on, and then the smoke generated by the straw went through the flask. Just like a technique of hookah. Are you familiar with hookah? Have you seen it? So the almost same principle is applied over here, and this is very old tradition of hookah. I have also seen in Egypt the people are very much fond of hookah, especially in the meetings. They like it very much. So similarly, the smoke was sucked by the pump, and the smoke was carried to the suction flask, and the smoke was dissolved in water. Okay. So first we turn on the induction heater, and the charring of wheat straw starts, and when the charring starts, it generates smoke. The smoke was sucked by the pump through the water. Okay. So the water will become yellow in color. Gradually it will be yellow in color. So after 5 minutes of operation of the equipment, we will take a sample by using a micropipette, and we take only 0.5 ml, that is 500 microliters of sample, and we will read in the spectrophotometer at 430 nanometers. Okay, 430 is the best optical density for reading the smoke water. Okay, so obviously the optical density is increased time to time. So after each 5 minutes, we take a sample of smoke water, we read the optical density, and a time will come when no more smoke will be dissolved in water. So this is called as SSW. When optical density is not increasing, it means that double distilled water is fully saturated with the smoke. Okay. Now you can use this SSW, that is smoke saturated water, for your experiment. Obviously, you have to dilute it because it is highly concentrated, and kerikins are required in very minute quantity, -8, -9 molar concentration. Very minute concentration is effective in inducing the seed germination and inducing the plant growth. So you have to dilute it. In our experiment, we diluted it 1 to 1000 dilution, 1 to 500 dilution, 1 to 250 dilution, and 1 to 100 dilution. Okay. So obviously 1 to 1000 dilution was the most dilute, and 1 to 100 dilution was the most strong, or the most concentrated, you can say, right? So we sprayed this diluted, saturated smoke water on plants, and different parameters were studied, and we found out that in most of the cases 10 power minus 8 m was the best concentration of smoke water in increasing the yield and growth and other performance and also seed germination. Okay. In some cases 10 power minus 9 m was also proved best. Parallel to this, we also worked on Carikin. Carikin was purchased from Alberta Chemical Agency from Canada, and this is very expensive chemical. As I told you that 1 milligram it costs 25,000 rupees. So for the sake of comparison, standard is must. So we purchased this chemical from Canada, 1 milligram Carikin KR1, and then we compared it. Also, we studied the effect of KR1 on the plant, and we took 4 concentration, that is 0, 10 power minus 9 m, minus 8 m, minus 7 m, minus 6 m. Okay. So in this way, we also studied the effect of smoke, water, and as well as effect of kerikins, right? So today I am going to demonstrate how it works, okay, and how you can prepare this apparatus, okay, at your own cost. So these are different parts of this smoke generating plant. This is induction heater of Philips company. So first you have to start at the full speed, then you can reduce it up to minimum, okay? And then smoke will be generated by the heating of this straw. Inside this utensil, there is straw. We first took the straw from a village, and then we washed it and dried it in oven, and when the water was completely removed, then we transferred the straw in this steel utensil, right? And then it was placed on the top of the induction heater, right? This was covered by a funnel, receiving funnel, okay? This funnel was connected by a plastic tubing. Tubing was carried to the suction flask, the suction flask. So this tube was connected to a glass tube, okay? Okay, and in the glass tube, the lower end was just above the bottom. So it should not be touched with the bottom, but rather 0.5 centimeter or 1 centimeter maybe above, so that the smoke can pass easily, right? Then we take the double distilled water in the flask, suction flask, and it should be measured. It was measured नहीं किया हमने, but you should take 1 liter of, exact 1 liter of double distilled water inside this suction flask, right? Now this is suction pump, okay? This is made in India, and this suction pump, basically this has a dual function. If you connect the connector with this point, this will suck the air, and if you connect the connection with this point, this will push the air, okay? So dual function. So now I am using this equipment for sucking the air as a vacuum pump, right? And good thing is that this also contains a regulator, okay? You can control the speed also. For example, 1, 2, 3, 4, 5, 6, up to 6 level, you can increase it. but normally we run it at either 2 or 3 point, okay, of suction pressure, right? So this is the power supply, and so now we start the induction heater. I think this is the connection of heater, and then we have to turn it on. This is power button, and then we have to deal it with a manual system. So first make it very fast heating like this, deep fry, that is about 200 degree centigrade. Now you can turn it off, and then you can decrease the temperature to the minimum level. Turn it on, go to manual, and then you can decrease temperature to the minimum. It is 120 degree centigrade temperature, right? So now it is burning and the smokes are slowly coming out, and it will advance also. And then we'll turn on this vacuum pump, and here is the button for the power supply, and then we have to make it turn it on. You can lock it also. You see? You see, smoke is forming, and now it is going to the water. So now the smoke is being dissolved in double distilled water. So it will become yellow. After each 5 minutes, you have to turn off the system. After 5 minutes, you have to turn off the system like this, and then after 5 minutes, turn on the system, and then take a micropipette, fix the reading at 500 microliters, and then open this bottle. This is attached with the cork. Open this like this, and take a sample from this water, and like this. Okay. So anyway, just we have to take 500 microliter of the sample, transfer into a spectroscopic tube, and read the optical density at 430 nanometer, right? Because what is the optimum maxima? This is the reading where the maximum OD comes. So we have to read all the readings at 430 nanometers. In this you will find a graph. After 5 minutes, 10 minutes, the optical density will increase. A time will come when there will be no increase of dissolving of smoke in water, and this will be fully yellow in color. Okay? No change in color will happen after this time. So at this time, you will get SSW, smoke saturated water. Now this water is ready for giving the treatment to the plant, right? So you have to dilute it first. Take 1 ml of this and 999 ml DDW. This will be a dilution of 1:1000, right? Then you have to take the second treatment. Take 1 ml of this and take 499 ml of distilled water. Dissolve it. This will be treatment 2. Similarly, for 250, you have to take 1 ml of this SSW and take 249 ml of DDW, dissolve it. This is treatment 3. The last treatment is 1:100. So take 1 ml of SSW and 99 ml of double distilled water. Check well. This will be treatment number 4. Now these chemicals are ready for spraying the plant. You can also study in hydroponics also, or tissue culture technique. You can use these concentration by different ways, right? So in this way, you can increase the speed. If the rate of generation of smoke is high, you can increase the speed. Okay? You can see the water is yellowing. Water is yellowing in color. So take a sample of 500 milliliters after 5 minutes. Okay? And make a graph like this. Okay? When saturation occurs, there is no increase in optical density, stop. And now your water is ready, called as smoke saturated water, SSW, and you can this use for your treatment. On the other hand, you have to take a sample of this water, and also you have to perform the LCMS, okay, to find out that which fraction, how many fractions are there, and which fraction is KR1. Okay, if you are working on KR1, you can find out the KR1 in your piece of the LCMS, right? Clear to you? Any question, any query, any objection? This is the slowest speed, number 1. And now I am going to turn it off. Okay? Clear? Any question? Any suggestion? If you want to ask, you are welcome. I will be happy if you ask questions. Don't shy. What will happen? No more smoke will be dissolved in water if you increase the time, because the capacity of dissolving of this water to the smoke is saturated. Okay, this will be wasted. All the extra smoke will be sucked and ejected from this outlet. So it will be useless to run the system after maximum optical density is achieved. Okay, you have to take sample each after 5 minutes. Okay, keep on taking optical density. When you find a saturation, stop it. Okay, because no more smoke will be dissolved in this water, and this is fully saturated. Now you can use it after diluting it 1 to 1000 times, 500, 1 to 500, 1 to 250, 1 to 100, etc. Right? Clear? Thank you very much.